Okay, so hello students. So this is your lecture number 6, and after doing your property 4 in the last lecture, that was regarding the Laplace transform of derivatives, that how we can find the Laplace of derivatives, and there also we did some of the questions that were related to the application of Laplace transform, where we solve the differential equation using your property number 4 and various other properties. Now this is the property 5 where we are going to find the Laplace transform of integral. So what this property is, so it says let fx be a piecewise continuous and of exponential order c for all x greater than or equals to 0, so that Laplace of fx is equals to fp. Then according to property number 5, if we have to find the Laplace of integral of this type 0 to x fx dx, then that value is given by fp upon p. So this is the property number 5 there, where we find the Laplace transform of integral that is 0 to x fx dx. And in general this property is written as, mostly we are going to use this thing, but still in general the property says that if you have this integral fx, this is n times, then you have dx, this is n times, then this is equals to fp upon p raised to power n. So this in general the property number 5, where we find the Laplace transform of your integral of the form 0 to x fx dx. Now see how we can use this property number 5 to solve the problems of Laplace transform. So let me consider your first problem. Find the Laplace of 0 to x cos hyperbolic x dx. Okay. So this is what I need to find, the Laplace of 0 to x cos hyperbolic x. So clearly, since here is integration 0 to x, so my property number 5 is going to be used in one or other way. So this is something like Laplace of 0 to x fx dx. That is what I need to find, and this is, or let me write it properly. Yes, here it is, where fx is your x cos hyperbolic x. So this is of this form, and by property of number 5 of Laplace transform, here we did it, this one, this Laplace is always equals to fp upon p. So using this property I can write that if this Laplace of 0 to fx dx, where fx is x cos hyperbolic x from here, then this is going to be equals to fp upon p, where fp is basically the Laplace of fx. So whole story now revolves around this fp, that how we can find this Laplace of fx, or how to find fp. So now once we got fp, we can put it here, and then the required result or Laplace will be there. So now we have to find fp, that is Laplace of fx, and fx here is x cos hyperbolic x. This is what we need to do. So this is what we have to find it now. Now I am not using the formula of cos hyperbolic, Laplace of cos hyperbolic as such, because students usually confuse that with the formula of sine and cosine. So it is better that we use the definition of hyperbolic function of cos, and that is ex plus e raised to power minus x by 2. So I can write it as half e raised to power x plus e raised to power minus x. This is what cos hyperbolic x is. So this is 1 by 2 Laplace of x ex plus e raised to power minus x, and then sorting the terms further, I will get here this equals to 1 by 2 Laplace of x dot ex and Laplace of x dot e raised to power minus x. So this is my fp or Laplace of fx that I need to find for getting the Laplace of the function that has been asked in the question. So now this is very simple. This is, you can see here the first shifting property. I have written it this form, otherwise it is something ex dot x. Instead of using the property x dot fx, it is always better to use first shifting property. So I am writing it as e minus x dot x, because then I can use first shifting property. Instead of writing this, then it is something x dot fx. So I need to use property number 2, x dot fx, property number 2. But it is better that I use shifting property, that is much easier. Remember that if I have to find the Laplace of this, since Laplace of x is 1 upon p square, so the Laplace by shifting first property, this is p minus 1 ka whole square. So I can write it now. Laplace of ex dot x is 1 upon p minus 1 ka whole square, plus Laplace of e raised to minus x dot x is p plus 1 ka whole square. This is, and if I solve it further, then this fp or Laplace of fx, that is Laplace of x cos hyperbolic x, comes out to be p square plus 1 upon p square minus 1 ka whole square. I solve this whole terms, combine these terms, and then finally I got this term, p square plus 1 upon p square minus 1 ka whole square. So this is fp that I was looking for to find the Laplace of this one, Laplace of fx, or that is Laplace of 0 to x, x cos hyperbolic x dx, that is equals to this one. I was looking for this thing, that is equals to your this Laplace. Let me just write it correctly. Yes, here it is, Laplace of this one. So this Laplace is equal to this one, and that comes out to fp upon p, and fp I have now found. So my result there is, therefore Laplace of 0 to x cos hyperbolic x, or x dot cos hyperbolic x, that I wrote like this one, and this was fp upon p, and now I have got the fp, that is p square plus 1 upon p square minus 1 ka whole square divided by p. So this is the result. And so in this type of question I need to just only divide fp. The main thing is to find fp, that is the Laplace of fx, and then you divide that fp with p. That will give you the desired solution. Okay, so again, now coming to another example related to this here, property number 5. Laplace of 0 to x, x dot e raised to power minus x cos 2x dx. This Laplace you have to find. Now clearly you can see here in this question, he is asking you something like Laplace of 0 to x, x dot e raised to power minus x cos 2x dx. This is what he is asking you, and it is of the form 0 to x fx dx. It is in this form, where fx is your x e raised to power minus x cos 2x. This is, and by property number 5, this Laplace of 0 to x fx dx is equals to fp by p, where fp is basically the Laplace of fx, and that is what we need to find. So only the whole story revolves around for this question to find the Laplace of fp, or the Laplace of fx. So fp, that is Laplace of fx, that we need to find is your Laplace of x e raised to power minus x cos 2x. So as we have discussed in previous examples also, it is always better to use the first shifting property in the end and use other properties instead. So I need to find this thing. Laplace of e raised to minus x dot x cos 2x. And here I can see two properties are used, x dot fx and then first shifting property, ex dot fx. So let us start from the extreme right. Since Laplace of cos 2x is your p upon p square plus 4. Okay, so Laplace of x dot cos 2x, property 2, this is minus of dy dp, or first derivative of this one, fp, of Laplace of cos 2x. And when you solve this, you will get here p square minus 4 upon p square plus 4 ka whole square. So this is what you get, the Laplace of x dot cos 2x. Now the last only thing is left is e raised to power minus x. Hence the Laplace of e raised to power minus x dot cos 2x is equals to change p by p plus 1 ka whole square, change p by p plus 1 ka whole square. That is here. So this is p plus 1 ka whole square plus 4 ka whole square. So this is your fp that we were looking for. Fp here, the Laplace, this we have got. So here is your fp, that was Laplace of e minus x dot cos 2x or fx, and this is what we got from your Laplace of fx. Done. Hence we got the fp. Hence the question that he was asking, hence Laplace of 0 to x e raised to power minus x cos 2x dx is equals to, it is your, here we have left the question here, you can see fp upon p, where fp is the Laplace of this one, and here we have found it now. So the Laplace of this is fp divided by p. So let me write it here as, this is p plus 1 ka whole square minus 4 upon p plus 1 ka whole square plus 4 ka whole square. So this is the fp by p form, or the Laplace of this integral that has been asked in the question. So this is how we solve the questions related to your property number 3. And here in this question especially, there were more than one property that has been used in this example. Now coming to the example 3, find Laplace of e raised to power minus 3x 0 to x sine square x upon x dx. So clearly you can see here, although the integral is, the whole function is not inside the integral, it is something like e raised to power minus 3x integration 0 to x fx dx. It is some sort of this thing where fx is sine square x upon x. So this is of this form. So first we need to work out the Laplace of this integral, because we always start from extreme right, and in the extreme right, and on the other term is your exponential, that is first shifting property, so we tend to use in the end. So it is better that first we find the Laplace of this thing. So to find the Laplace of this thing, we know that the Laplace of 0 to x fx dx is equals to fp upon p, and fp is the Laplace of fx. So again the story comes around the finding the Laplace of fx. So since fx is your sine square x upon x, so fp or Laplace of fx is equals to Laplace of sine square x upon x. That is what we need to first find. Now again you can see here we have a again use of the property number 3, fx upon x. So since first we start with the Laplace of sine square x, and for sine square x we need to change it into the form of cos, that is 1 minus cos 2x upon 2. Yes, here it is. That is Laplace of 1 by 2 minus 1 by 2 Laplace of cos 2x. So this gives me 1 by 2 p minus p upon 2 p square plus 4, the Laplace of sine square x. This is your Laplace of sine square x. If the Laplace of sine square x is this one, so we need to find Laplace of sine square upon x. So by property 3, Laplace of sine square x upon x is p to infinity 1 upon 2p minus p to p square plus 4 dp. Yes, here it is. Either we can take 1 by 2 common. So when we solve this integral, I'm just starting directly the result. It comes out to be 1 by 2. We have done these type of integrals. Usually when you solve the integration, then after that you get infinity minus infinity form. So you change it into the log form. So it is ln under root p square plus 4 upon p. This is the required form that you will get for the Laplace of sine square x upon x. So we were looking for the Laplace of 0 to x fx dx, where fx is your sine square x. We need fp, the Laplace of this one, sine square x upon x, and we got that. We got the Laplace of sine square upon x. So now we can find the Laplace of 0 to x fx dx, and that is simply fp by p. That is simply fp by p. So Laplace of 0 to x fx dx is equals to fp, that is here, this is your fp, and 1 by 2 ln under root p square plus 4 upon p whole divided by p. So this is what your result for the Laplace of 0 to x sine square x upon x. So how we started? We find the Laplace of sine square x, then we find the Laplace of sine square x upon x. This is how we proceed. We first find the Laplace of sine square x. Here it is, Laplace of sine square x. Then we find the Laplace of sine square x upon x, and then third property, property number 3, Laplace of 0 to x. And hence the question that he is now asking, the Laplace of e raised to power minus 3x. The question was actually this one more property of first shifting that is going to be used. So we just need to change p to p plus 3, ln change to p plus 3. Yes, here it is. So this is the required solution of the given question, where you find the Laplace using various properties, and Laplace using various properties. First shifting property was used here, property number 3, division by x was used here, and also property number 5, where you have to find the Laplace of integral of the form 0 to x fx dx, that was used. So this is how we solve the questions of your this related to your property 5, and no doubt in this question various other properties has also been used. Now I am coming to the inverse Laplace transform of property 5. Inverse Laplace transform of this property number 5. So if Laplace of fx is equals to fp, no doubt p is greater than c, then we, by the property number 5, Laplace 0 to x fx dx is equals to fp upon p. So this is what we have done in the property number 5. So Laplace inverse of fp by p is equals to integral 0 to x fx dx. So this is the inverse of Laplace property of number 5. Laplace inverse of fp upon p is 0 to x fx dx. Also you have the relation that Laplace of 0 to x your fx dx, this is n times, this is again n times, is equals to fp upon p raised to power n. So here, Laplace inverse of fp upon p raised to power n is equals to 0 to x fx dx. This is n times and this is n times. Yes. So here it is the Laplace inverse of fp upon p raised to power n. So now we will see how we can use this inverse in various questions. But the more important thing is that the questions that are to be solved using this inverse property can also be solved either by partial fractions and by convolution theorem that we will do later. So we will not be going in much depth of this inverse of this property because most of the questions from that can be solved using this property 5 that can also be solved easily even by partial fractions or convolution. However, we will just see how we can solve the inverse problems of Laplace transform using using the inverse of this property. So say you have to find the Laplace of this one, inverse of 1 upon p square upon p minus 2. So clearly you have here Laplace inverse. This is your Laplace inverse, say gp, and gp is your 1 upon p square p minus 2. Now I can write it like, to correlate with property 5, I can write it as p minus 2 upon p square. Now this is of the form fp upon p square. I will always be taking fp whose Laplace transform I know that this is value whose Laplace transform I can easily find. So here fp is your 1 upon p minus 2 and I know it is e raised to power 2x whose Laplace transform it is. So this is the Laplace inverse he is asking, and now I change it into this form and this correlates to property number 5. And according to property number 5, this is going to become 0 to x fx dx double integral because in the denominator it is p square. So this is what now I have to find where fx is basically Laplace inverse fp. So again the thing is to find the Laplace inverse to find fx, and here in this case fp, as we have written above, 1 upon p minus 2, and this is e raised to power 2x. This is, so put 2 here, you get 0 to x e raised to power 2x dx. So solving this integral twice, you will get e to x by 2 minus x minus 1 by 2. You can solve this calculation and verify these results. So this is how. So in these type of problems of your Laplace transform, where you can use property number 5, you just have to identify whether you can write the given fp or gp, whatever is given, in some form of fp upon p raised to power n, such that this fp is easy to work with or to solve, because only this will be going to give you fx, as fx will be Laplace inverse of fp. So this fp should be easy one so that we can work the problem easily. And also this question you can see can be solved easily by partial fractions also. It is not like that we can solve only this question by this property. If we use this, you have p square upon p minus 2. So by partial fractions, this becomes your minus 1 by 4 p minus 1 by 2 p square plus 1 by 4 p minus 2. Yes. So clearly you can also use the partial fraction. You have to work out little bit for making the partial fraction, but now you can easily solve or take their integrals. The result are going to be same. They will not vary. So this is how we solve these problems. And let me do one more problem related to this property number 5. This is your Laplace inverse. of your 1 by p tan inverse 2 by p. This is what I need to find. So clearly this Laplace inverse I denoted by GP is given to be tan inverse 2 upon p by p. So this is again the form Fp by p, the form of property number 5, where Fp is your tan inverse 2 upon p, and by property number 5 this is going to be 0 to x fx dx. So I need fx to go further to solve this integral, and fx will come from this Fp, Laplace inverse of Fp. So this Fp is basically Laplace of fx. So fx will be Laplace inverse Fp. So this is what I need to find. So fx is equals to Laplace inverse tan inverse 2 by p. That is what I need to find now. Only then I will be able to get fx. So clearly here your term that we need to find is your, say this is your, I need to find here Laplace inverse of Kp, and Kp is your tan inverse 2 upon p. So by looking at this I can see it does not correlate with any of the form that we have studied. So what we can do, this is Laplace inverse, I am writing it Kp, sorry for that, it is, we have considered it earlier, this is Fp not Kp. I need not to take another variable, it is already taken Fp, and Fp is your tan inverse 2 upon p. So I need not to make another variable, choose another notation for this tan inverse 2 by p. So for such type problem we did earlier, we need to take the derivative. If no manipulation works, just try to take the derivative, and in this case the derivative with respect to p of tan inverse 2 upon p, I am writing it directly, this is your, comes out to be minus 2 upon p square plus 4. So this is the derivative of tan inverse 2 upon p, and now this correlates with the Laplace inverse of sine. So now I take the Laplace inverse of f dash p. This gives me Laplace inverse of minus 2 p square plus 4, that is minus 2 Laplace inverse 1 upon p square plus 4, and now okay, so now this gives me directly equals to minus 2, this is sine 2x by 2. So this is simply your minus sine 2x. So I got Laplace inverse of f dash p is equals to minus sine 2x. This is equation number 3. I don't know what equations I have taken earlier. So it is 1. This is, I can take 2. This I can take as 2. Now I need, but what we are going to do, we are looking for this fx, and this fx will come out from the Laplace inverse of this one. Okay, so now we have found Laplace inverse, and that is equals to minus sine 2x. So this minus sine 2x is basically the, just hold on, yes, here it is f, we have got your, this equals to minus of sine 2x. So just wait, we are just confusing a bit. Okay, so again coming back to this problem, we need the Laplace inverse of fp, and here we have reached up to this where we have found the Laplace inverse f dash p, and also we know that the, from the Laplace inverse of property number your 4, it is equals to minus x fx. I was a bit confusing that this, I was just forgetting that this is f dash p. So this was a confusion, was a thing that was confusing me. This is the Laplace inverse of f dash p, whereas in the question we need Laplace inverse of fp. This is fp. This is fp. So I was just confusing it with f dash p. So now from 2 and 3, I got minus x fx is equals to minus sine 2x. So this implies fx is equals to sine 2x upon x. Sine 2x upon x. So this is what you have got your fx that we need for this Laplace inverse tan inverse 2p. This is the fx required that we need to put it in this integral, because our actual question was to find the Laplace inverse of this one, which we wrote like fp upon p. Fp is this one, and that comes out basically in the form of 0 to x fx. So all story was around finding this fx, that is Laplace inverse of this tan inverse 2 by p. And there, since tan inverse 2p was not in the form that we can sort it out easily, so we differentiate it. We take the Laplace inverse, and then using the inverse property of your inverse of property number 4, we wrote it like this, compare these two, and then we got the value of fx. So the Laplace inverse of your tan inverse 2 upon p, that was equals to 0 to x fx dx, has given in equation number 1. So we have now found fx. So this is 0 to x sine 2x upon x dx. So this is the result, as this integral is not solvable. You can see this is sine x or sine 2x upon x in form. So we can't solve this integral, and we have to leave this question. If it is there, then we have to leave this question up to this form. Don't try to solve this integral, because this is x in the denominator and it is going to become 1 upon x square if you use the integration by parts. So these type of question if come, we have to leave it up to here. So this is the required solution for fx. This is required fx. This was your Laplace of gp that you wrote like fp upon p, and here you got your gx, not fx. I should write here gx. I got this for this gp, I got this gx, and that is your this integral. Okay, so with this this your property number 5 and inverse is now complete, and after this we will start your convolution and convolution theorem and second shifting property. Okay, thank you, thanks a lot.